This is ELiC, efficient LiDAR geometry compression via cross-bit depth feature propagation and Bag-of-Encoders. We present a neural codec that delivers real-time encoding and decoding while achieving state-of-the-art compression on LiDAR point clouds. This work was conducted by Junsik Kim, Bang, and Soowoong Kim from ETRI, Korea. LiDAR has become a core sensor for autonomous driving, V2X communication, and digital twin application. However, LiDAR geometry compression faces three key challenges. First, the data is massive, creating storage and bandwidth bottlenecks. Second, at high bit levels, the point cloud becomes extremely sparse, which breaks local spatial context and makes prediction difficult. Finally, real-time systems require fast processing under strict compute constraints. Together, these factors make it hard to achieve both efficiency and real-time speed simultaneously. To address these challenges, we propose ELiC. Our approach is based on three key ideas. First, we reuse information across bit depth levels through cross-bit depth feature propagation. Second, we adapt to different data distributions using a Bag-of-Encoders strategy. And finally, we reduce computational overhead with the Morton-order hierarchy. Conventional methods process each bit depth level independently. As a result, they redrive spatial context at every level, which becomes unreliable in sparse high bit depth regions. In contrast, our approach reuses features from lower bit depth levels and propagates them to higher levels. This allows the model to maintain rich contextual information even in extremely sparse regions. This is the key idea that enables robust prediction even in extremely sparse geometry. Another challenge is that data distribution varies across bit depth levels. Each level has different occupancy patterns, so a single encoder cannot perform optimally. Different bit depth levels require different model capacities. To address this, we introduce a Bag-of-Encoders. We prepare multiple encoders and select the most suitable one for each level. This allows the model to better adapt to varying distributions. Finally, we focus on improving computational efficiency. Conventional methods require sorting at every bit depth level, which introduces significant overhead. Instead, we maintain a global Morton order across all levels. This eliminates repeated sorting operations and enables efficient hierarchical processing. As a result, we significantly reduce runtime. We first evaluate runtime efficiency. ELiC achieves the fastest runtime among all methods. On average, encoding takes only 0.121 seconds, and decoding takes 0.111 seconds per frame. This is significantly faster than traditional method while remaining competitive with learning-based approach. Next, we evaluate compression efficiency. On the Ford dataset, ELiC largely achieves the best performance. On SemanticKITTI, it achieves compression comparable to the state-of-the-art. Overall, ELiC provides the best compression runtime trade-off. This shows that ELiC achieves both efficiency and performance simultaneously. We perform ablation studies to analyze each component. Even without the Bag-of-Encoders, our cross-bit depth propagation alone already outperformed Leno by 8.6% on Ford dataset. This shows that feature propagation alone provides substantial compression gains. Adding Bag-of-Encoders further reduce the bitrate, and as the qualitative results show, both components consistently produce more compact bit allocation, particularly in sparse regions. We also analyzed the effect of the Morton-order hierarchy. When replaced with explicit per-level sorting, encoding latency rises from 0.121 to 0.142 seconds, and decoding from 0.111 to 0.128 seconds, about a 55% increase. This confirms that eliminating sorting overhead is critical for real-time performance. In conclusion, we presented ELiC for efficient LiDAR geometry compression by reusing information, adapting to distributions, and removing redundant computation. ELiC achieves both high compression efficiency and real-time performance. ELiC bridges the gap between efficiency and real-time LiDAR compression. The code is publicly available, and you can access it via the QR code on this slide. Thank you for your attention.